All right. So now we have to write a word equation for where the pot's energy goes, right? So
Yeah.
what happens? Is it energy in the water? What is heated here?
The water, the teapot and the water too.
So the water's temperature has reduced and the teapot's temperature has increased, no? So we have to kind of
Uh,
look into the situation and identify where the heat has flowed. Can you tell me?
right. So it's gone from the water to the
Exactly.
teapot.
Good. So energy lost by water equals energy gained. mm, ah, Energy gained by teapot. No?
Yeah.
Right. So this we already know as 15288. That's the energy lost by the water. Then that energy will be gained to the teapot, but now we need to find the C of it, right? So instead of this, we will write mass times C unknown. Mass is given as 0.43. C is unknown, and the change in temperature, it has gone from 22 to what is final temperature of the teapot?
80, 81, right? So
51,
that's 59.
59, no?
Yeah.
So 59. So then you can see we can solve for C over here. Okay? Um,
Yeah.
Hundred two joules per kilogram Kelvin. We can write like this, no? Joules per
Yeah.
kilogram per Kelvin. Um, okay, let's put what's a legitimate question. Accepted value for the specific heat capacity of stainless steel is 500. Compare this with the value you have calculated and explain the difference. Hmm. So this is how do you compare?
Well,
If we calculate a percentage difference,
that might be a good, easiest way to do that.
yeah. So we can put 602 minus 500 over the standard value times 100. That would be 102 divided by 5. That is 20.4% higher than uh, accepted value. For 1 mark,
Yeah.
perhaps not necessary, but I don't want to take any risk. So I would personally do the percentage answer, sorry, difference, since it's such a small thing. Then
Yeah.
after that you can say why though. So if you look at the equation, what we solved, you put 15,288 divided by that mass.
0.43 times 59.
So what is the value here? That has messed up now. What? Yeah. What do you think? Just looking at it basically, which value has caused this thing to you know
Yeah. Um, uh, it could be actually the temperature.
Yes. Yes. So the temperature rise is this too small or too big?
Uh, is it? Yeah, I would say it's too big.
Okay. Now, what you were supposed to get was 500. You got 600. So the C that you got is bigger than expected. So to make this big, this one is smaller than actual, no? Too small.
Yeah, actually, you're right. Yeah.
Yeah. If we make this like 65, then the value of C calculated will become lower and closer to 500. So this is too small. Why is it too small?
Hmm.
Because
Yeah, because the energy has escaped into the surroundings.
so some of the thermal energy that should have gone to the teapot has escaped to the surroundings. Yeah. So you can see temperature rise because, no? Because temperature rise of the teapot is too low due to energy escaping to the surroundings. We don't have to write
Yeah.
it, we can just discuss verbally.
Yeah, exactly. But because we're here, can we speak now why, as in, it's a stainless steel pot, right? Energy is escaping. But how would we, let's say, I guess we would measure this temperature with a thermometer,
Yeah,
right?
yeah,
And then we just do it over in, if we wanted to get better results, we could take it like at certain intervals and then plot a graph of
very nice.
temperature over time.
That's true. That's true. Very good. So you've been reading the Hodder book, no?
Yeah, I don't know how much I retain, but I try and read.
That's great. That's great. That's actually fantastic point. Yeah. So it will start off the as the heat makes its way through the teapot. There'll be a small the rate at which temperature rises will be low because the heat is still kind of moving from the water to the thermometer connection place. After that, you will see a steady rise, and then as the teapot gets too hot, you will get a lot of energy escaping to the atmosphere, causing this kind of change. So, if you can focus on the linear section and get, like you said, change in temperature over, no,
Time.
what? 1 second. C equals E over MC. Sorry, C equals E over M delta T. Oh, okay. Here we have a problem because we don't have time in here, right?
Yeah.
But in a different case, if you were supplying like to a blob, sorry, not a blob, into a cylinder of into a cylinder of steel or something with a electrical heater, then you can have time. So because
Yeah.
this electrical energy will be VIT. So VIT equals MC delta T. So you can do like this VI equals MC delta capital T over time. So you can identify that and substitute the gradient from here into here. But in the teapot case that we are discussing, time is not involved. So we can't really use the graph. What you can do is add insulation around the whole thing to kind of reduce the energy loss, right?
Yeah.
All right. Question. We have something. I think I saw it out of the corner of my electrical power generated by nuclear something something. Energy needs, however, Rutherford, who is credited with the discovery and first splitting of nuclear atom, later said energy very poor kind of thing. Anyone who expects a Source of power from the transformation of these atoms is talking moonshine. Okay. Rutherford carried out experiments that involve firing alpha particles at nitrogen atoms. Okay. Now this is I'm sure there's a binding energy type of question here.
Yeah, there is.
No, there's energy released by fission. No,
Yeah,
that's fine. So that also we can actually cover now. As we go to,
yeah,
let me see whether there are any other specific heat capacity questions. No, we have a nice mixture of thermodynamics questions here. So we'll actually take a look at it. Yeah. All right. We can just fill that in. Just do overall revision.
yeah. So that's 1 0. So that means wait. So oxygen is 17. 17 on the top, and then 8 at the bottom,
Because this is one,
and then
no?
1. Yeah,
All right, nice. Interaction requires a small energy input. Other similar nuclear reactions may give an energy output of no more than 20 mega electron volt. Okay. Interaction requires a small energy input and it has output of 20 mega electron volt. That's a unit of energy. Giving some
yeah.
justification to Rutherford's statement. Suggest why Rutherford's statement eventually turned out to be very inaccurate. Now I put this in the study points that I sent over WhatsApp. So even though the energy released by one fission event is very low, if there is a chain reaction causing, a large rate of fission, then you can obtain, like if there are many fission events, all that 20 mega electron volts will add together and give a big energy, right? So you need to communicate that idea for 1 mark only. So very small amount of stuff is required. We can say um, if reaction rate is high, um,
The camera got stuck.
this thing really knows how to. Okay, anyway, while I'm resetting it, I'll say something. So, yeah, if the reaction rate is high, there are many nuclei undergoing fission. So, um, wait, once again. Okay. So the overall amount of you can produce a high power, right? If there's a lot of reactions per second, basically. Um, okay, let's see what's wrong here.
That's the point. It's like there's a lot of energy being released in fission reactions, and they form, and the result of the first fission reaction is a further chain reaction, right?
Yeah,
So that's why he was wrong.
yeah. But no, actually, Rutherford only considered the effect of one fission event, but he forgot that. Not forgot. He has not considered the possibility of a large reaction rate, right? Because he only tried it with probably one atom. If you have a enriched source of uranium or something, that can. And that brings us to the next question. Uranium 235 is able to undergo fission without such a stimulation. Now, Rutherford had to shoot it with a alpha particle, but uranium can undergo chain reaction if you put up like some neutrons, right? Because it produces more neutrons. You can see we give one neutron on the left side, but on the right side it produces three, so which will go and strike more uranium, continuing the process. Energy released by fission. Do you remember the overall procedure here?
Let me see.
Masses are given. So from there,
Yeah. Yeah. Actually, I remember the like to begin with. I remember the formula, right?
Wait.
So
If it takes you this long, I don't think you remember the formula.
I do, It's energy of uranium, or energy supplied rather,
Hmm.
plus energy of individual nucleons is
Yeah,
equal to total energy.
yeah. But now here we are not dealing with any kind of kinetic energy. So basically, only the mass terms remain. Like you're talking about Ek plus mc square initial, Ek plus mc square final, right?
Yeah,
We are not dealing with kinetic energy, so we are essentially dealing with a mass change. So if you can find the mass deficit, then you're good to go. That is the principal guiding thing of this. So now, which side has more mass from the theory? Shall we recall and see? Is it the left side or right hand side which has more mass from what you know? Any quick answer?
uh, yeah, I would say right side.
Right side has more mass or less mass?
Wait,
Sorry, I
energy is released to form mass. So
energy is released. Okay, so the mass.
forming mass. So the mass on right side is bigger.
What are you saying? To produce energy, you need to destroy mass.
Yeah,
So the right side will be smaller. Is that?
yeah, that's true.
Let me connect it to the this graph also, the binding energy per nucleon graph. Now,
Yeah, the camera is not on, but
it's not on. Okay.
no.
Yeah. So, yeah. Earlier, what I was saying is in this, the kinetic energy terms are getting cut because we are not dealing with kinetic energy. So, we are essentially dealing with a mass deficit causing energy. So, energy to be released. We know uranium is here, and uh, the most stable, the most stable place to be is over here. Like it is a isotope of iron, uh, the metal iron. So the higher the binding energy per nucleon, the more stable it is. So these ones like uranium, cerium, these radioactive isotopes are unstable relative to this one. And then something like helium and hydrogen is also unstable compared to this point. So these ones want to fuse together and make bigger molecules so that they can be in this, come closer to this ideal position. These ones nuclei are big. They want to break and become smaller nuclei which have more binding energy per nucleon. So in this
Yeah,
case, uranium 235, which is going to go this way. And for that, it's going to release energy. As it becomes more stable, it's going to release energy. No?
yeah,
That's going to be released by destroying mass. We'll confirm this idea and we'll adapt the right side. Okay.
yeah,
Uh, Mass on right hand side equals. Um, so we are dealing with one krypton, one barium, and three neutrons. Let's adapt those. That would
yeah.
be 152.678. Yes. So we're dealing with 393.66591. Then mass on left hand side would be one uranium and one neutron. That is That is 300. Was I wrong?
No, the difference is like a point something, a decimal.
Maybe maybe this is there's some error in this. Let me recalculate that. Krypton 152.64708 64708 plus 233,99404 plus 3 times 1.67493. Wait, that mass is to be destroyed. Oh yeah, 391.66591. Okay, I know.
Yeah.
391. Okay, okay. But clearly you can see left hand side is bigger, right hand side is lower. Like I said, the mass is destroyed. No, mass has been
Yeah.
destroyed. So the delta n c square will be the energy. So we are dealing with 3 into 10 to the power 8, that's c square times this difference. Huh?
Yeah.
And, so that is 0.891. Is this in kilograms? No, we have to use the times 20, 10 to the power minus 27.
Yeah.
Reason I noticed is that this is not, it will be like 300 grams. So I was wondering how the hell is that possible? Right? 3 into 10 to the square times 0.30 times 10 to the power minus 27. Yeah. Yes. 2.78. We can give the answer to many decimal places because we have a lot of significant figures here 1, 2, 3. No, lowest number was in neutral 1, 2, 3, 4, 5, 6. You can give to 6 significant figures. This is definitely possible.
Yeah.
Yeah. We need to show it in mega electron volts. They have said no. Show it that it's a
Yeah.
170 mega electron volts. So you have to convert this. No? Mega electron volt. That means divided by mega 10 to the power 6 electron volt 1
Yeah.
10 to the power minus 90. So divided by brackets 10 to the power 6 times 1.6 times 10 to the power minus 90. 173. That's very good.
Yeah.
Then, but you get the idea, right? During fission and fusion, both the particles, the objective is to become more stable. So when stability is reached, energy is lost, and as in energy is created and shipped out to the atmosphere, and that energy comes from destroying mass. Then
Right. So the uranium would it wants to become more stable. So in order to get in order to do that, it has to wait. Um, basically there's strong nuclear forces that need to be broken, right, for it to undergo uh,
Do we want to
fission.
that level when we have the binding energy per nucleon graph? I don't think so. Now, when we are talking about binding energy per nucleon, that gives a clear idea of what is stable and what is not stable. So, uranium is not that stable compared to krypton and barium. Krypton and barium are all rather both closer to
The peak.
yeah, they're closer to the peak and barium are here, while uranium is over here. So they are both more stable. So we are moving in this direction basically. Beyond that, we don't want to go into the nuclear forces. Now, when it comes to binding energy, you might want to go into the nuclear forces. So let's say if I'm considering helium, which is two neutrons and two protons. So if you take neutron, neutron, proton, proton, and compare it with one nucleus, then this mass would be lower than this mass.
Yeah.
That's because this is unstable compared to this one. So when going from here to here, energy is released by destroying mass. Then if you want to break these nuclear forces, then you have to give it energy for it to use that energy and create the mass required to come back to this. This is a natural thing. This one is an unnatural thing because this is what happens in nature,
Hmm.
right? This is what is artificially done by human beings. If you accelerate a particle and hit it like smack dab in the middle, you would have to supply energy to break the bonds, and that energy can be calculated. Now, since these masses are different, the energy difference is that you would have to supply to break the nucleus into its constituent nucleons can be calculated from the mass deficit between these two times speed of light. That's where you would go to the nuclear forces, right?
Right. Yeah. I got it. I think no, but the main thing was getting the idea clear about energy being released to become more stable by destroying mass.
Yes.
Yeah.
Apart from I think this is mixing with unit for circular motion, and then later it's mixing with the specific heat capacity. Very nice. All right. One similarity, one difference between nuclei of uranium 238 and 235 isotopes. So we can easily say, I think, you know the similarity, no?
Yeah, they have the same. Oh, okay, that's quite simple. They have the same number of protons but different number of neutrons.
That's correct. Rotor has a diameter of 30 and at a rate of 60,000 RPM, centripetal acceleration. Captured with centripetal acceleration. So this is circular motion, classic circular motion. Now from RPM, we have already practiced. The key is to turn it into radians per second. That is our omega. Once you get the omega, you can calculate the centripetal acceleration by taking this is r omega square, no? Also v square over r.
Yeah.
This is the data equation sheet.
Yeah.
One, I hope you know how to calculate. It's 60,000 watt per minute. So 60,000 revolutions, you have to represent it. Angle. This you have to represent
Yeah.
it.
It's just yeah.
And this is
Exactly.
speed. And you can get it as 2005. 2005 radians per second. Once you get that, we can now multiply with this value and get radius. Yeah, tell me radius.
Um, wait. We got omega square. Wait 1 second.
No, no. From the question, tell me the radius.
Oh, that's 15.
Because diameter. I was checking whether you are paying attention to the. Uh,
That's good. Yeah.
yeah, that's meter. Don't worry about units. We are using standard units, so we will get.
300 pi.
No, this has to be squared, no? I was just looking at
Yeah.
this. I'm only getting s minus 1. I was wondering because this is s minus 2, no?
Yeah. True.
Yeah, so you square that, calculate, it's not a big deal. Rotor is subject
No.
to forces. Give two mechanical properties essential for the material from which the rotor is made. This is asking for unit 1 actually, and little out of syllabus also. That means
Yeah.
the strong and probably
Stiff.
strength is related to ultimate tensile stress. That is still there
Hmm.
in syllabus. Wait, you are in the old syllabus, no? Shit.
Yeah.
Okay, okay. So then for you it's there. So strength refers to the ultimate tensile stress that it can bear without breaking. So that's there. And then I think toughness also. Toughness refers to the amount of energy it can absorb um, before fracture. So the people in the new syllabus can identify this, the breaking point, the breaking
Hmm.
called ultimate tensile stress. If something has a high ultimate tensile stress, it has a high strength. Then if the area under the graph is high, that's a combination of a large extension before fracture and high Young modulus. Those two combinations give a large surface area, which is if this is a stress versus strain graph. Then this is a energy density. It can absorb a lot of energy per unit volume. That's what energy density is before fracture. So that's called toughness. But you can, since it's state, old syllabus guys can just say you know, high strength and high toughness. Yeah.
Right. Yeah.
Mm, okay. Part D, we have a calorimetry question finally, where you get to use MC delta T. But here you don't have mass, you have a flow rate. So when that happens, there are different approaches that different students take. Um,
Right.
As we see, we take a look. So that the rate at which energy is removed from the reactors is about 3000 megawatt, and hence estimate the value for efficiency of electrical power generation process. Okay. So now you can either find the number of joules that is transferred from the reactors to the water, or you can work with the equation. What do you prefer to do? Like, do you find the energy per second? Like, do you consider time to be 1 second and solve everything, or do you just do the equation?
Uh, I'm not sure actually.
What would you do? What would your like natural strategy be?
Since as in the right.
Yeah. What would be your like strategy? Now we know that specific heat capacity is given. It has to do with this equation.
Yeah.
Yeah. What would you do? Would you substitute
So we need.
what you can find? Maybe.
Yeah. I would say that's would be first thing because there's relatable quantities.
Yes. So then here we don't have mass. We have mass flow rate. So would you just put that value? Probably, no?
Yeah, I would because as in energy times time is equal to power. No, but
Yeah. So a lot of somebody who is into the math might do like this: divide both sides by t, and you know. So this is nothing but power, energy over time equals mass flow rate. That's
Yeah,
what mass flow rate times C delta T. But you can also
yeah,
consider 1 second, this much mass is there, and then do the calculation in 3990 times delta T is 11. So we get that answer. About 3000
right.
mega.
Yeah, is delta T given?
I thought you picked it up.
But
See, while you are reading, as soon as you know, like now I scrolled down and I saw specific heat capacity. So immediately I knew what equation. Then when I was reading through the question, I quickly picked out the numbers which are needed for this. So you need to, that is the key to actually scoring in calculations. When you look at it, you have to figure out what topic, what equation, right?
yeah,
Okay, times 3990 times, that is about 3000 megawatt. Yeah, it's 3072 megawatt actually. 3072 megawatt. Now we have to find the efficiency, no?
yeah.
Yeah.
So that's
The efficiency equals
3072 minus 2200 over 3072 times 100.
wait. Isn't it useful energy output over total input or rather energy input? Now, once it leaves the reactor, the that's what we are calculating for. So on top, you should just put 2200 because that is the electrical energy capacity. No, that is the output power is given, right?
Yeah,
Its output power is 2200. So you wouldn't subtract here, right? If you subtract, what you're finding is the power wasted, right? Useful. That means
right, yeah,
energy input. See, that's the energy input. Um, Energy input is 3000. What was it? And 72.
uh, yeah,
The useful energy is 2200. So if you subtract this minus this, you are finding the waste power. That's not what we want. We want the useful power. So that is divided by 3072 into 100 to give the answer of that's 72%. And that's what they are asking for, I think. I estimate. Wait, 1 second. Let's get it. Sorry.
where did you find the input temperature?
Sorry.
Where did you find the input temperature for the equation?
Input
You
temperature
said you picked it up.
or the temperature rise.
Temperature rise.
Yeah, so
Is
the
that 11K?
water is heated to approximately 11K above the input temperature.
Yeah,
So that's directly
yeah,
telling
that's a rise.
how much it increased, no?
Yeah,
Okay. Yeah, now we have a next question is about coals. Walking on hot coals without getting burned. Psycho people. Um, yeah, walking across hot coals without getting burned seems impossible, especially when the temperature is 1500 Kelvin. As long as they do not take too long to walk across the coals, firewalkers won't get burned. Explanation may have something to do with the relatively small amount of thermal energy involved. Although coals are hot, total amount transferred small. Like quenching a red hot metal by in trough of cold water. Metal cools rapidly, transferring thermal energy to water, but the rising temperature is quite small because of the relatively large value for the specific heat capacity of water. Okay, that's just some background. Describe an experiment you could carry out to measure the specific heat capacity of a metal, assuming that you have a number of metal washers which can be heated to a known temperature in a Bunsen flame and plunged into a container of water. State the measurements and the theoretical basis for the calculation you would carry out. So they have clearly said, describe the experiment, then state the state the measurements and the theoretical basis. What assumption would you make in calculating? So those are the clearly they have told us what they want now. If you read deep into the like not deep, if you read kind of into the question, you can understand from those things. So what do we need to do? We need to heat it like that's already given, isn't it? Okay, heated to a known temperature,
Yeah.
plunged into a container of water, that is already given. So then we can say measure the, we'll just write and see whether we have enough marks. Then if not, we will add some padding.
Yeah, the camera stuck again.
But yeah. Okay. So actually, yeah, can you start?
Yeah, I'll do that.
Start means verbally.
Right, okay.
What do you need to measure? Let's start with that.
Yeah, we need to measure the mass of the washer.
Very nice, very nice. Okay.
And right, also we have to measure the temperature change, as in the temperature initially of the water, and then after, yeah, after the washer has been put in it.
That's right. Now, what are you basing this on?
The equation E is equal to mc delta theta.
That's right. But then, did you make a like a thing in your mind that energy lost by, energy lost by washers equals energy gained by water?
That's, well, no, I didn't.
So the temperature rise of the water can be measured. Okay. Then.
Um,
Yeah, hold on. Let me just this app is not working. Right. Let me go back. Okay. So yeah. So you said mass of the washers. That's great. So if we think about that word equation now, because we are again that metal and or rather two materials mixing, that's what we're having here, right?
yeah.
Always useful to have a word equation. So energy lost by washers equals energy gain by water. So we need the mass of the metal. I don't put W here because I want to put W there. Mass of the water.
Yeah.
Times C of the metal times that is See, to calculate the temperature change of the washers, you need the initial temperature of the washers, which is already known because it's said in the question. Right? Assuming that you have a number of metal washers which can be heated to a known temperature and plunged into a container of water. Right? Heated to a known temperature. So that is already given.
Yeah.
We call T1. That will fall. So we have the final temperature of the mixture minus the initial temperature of the washer. But what about energy gain by this? That's mass of the water times C of the water times. By the way, we have to explain this.
Yeah, this is only an introduction in the question.
Yeah, no, it says give a theoretical basis of the calculation that you would carry out.
Right, so that would be this part here. The energy lost by washers is the energy gained by water.
Without knowing this, it's hard to know the measurements to take. No? So, measure mass of washers, mass of water, then final temperature of mixture.
Yeah.
And for this one, we need something else. Can you get it?
Final minus initial. So T.
Suppose
Yeah, it can be anything.
huh?
It can be T.
Without
That's already there.
without struggling there, why don't you think about what you're putting in here? There is a change in temperature of
The mixture.
not the mixture. This is mass of water. And here is it. We are writing the equation for energy gained by water. So we are looking at the temperature gained by water. No?
Yeah.
See, the whole point of writing the word equation is so that our mathematical equation is guided.
Yeah.
So energy lost by washers, you took them. Everything has to do with the washers only. Mass of washer, temperature loss of washers. So it might go from 1500 Kelvin to like I don't know 400 Kelvin. That might be the final temperature. That's about I don't know, can't be. More likely to be like 330 Kelvin. So yeah, this is the amount of temperature reduction of the washers, right?
Oh, so then it would be into T. Because now that won't there be wait, energy gained by water? So
See, let's build the skill here. 1 second. Oh, do you mind? Do you mind? Huh? All right. So, like you put down the equation to guide your thing. So the energy lost by washers. If you think about it on its own, then it's like if I provided you these values, you would do it immediately,
yeah.
So yeah, you need to apply the knowledge gained by the previous questions and apply it here. So you have to know the initial temperature, which is high value, and the final temperature, which
Yeah.
is a lower value, and that difference is what you will put in here. So
Yeah. Oh, so then this would be T final minus T initial.
yeah, But would this initial temperature and this initial temperature be same?
Mm, no. So then we can say like, yeah, like that, give variables.
But then we have to define all things that we are using, no? Because these are all things that we, or you have to
Yeah,
mention it here. M of the metal, M of the
yeah,
matter, then this is the F, then you can mention this initial temperature of washers, initial temperature of water. Then assumptions.
right. So that's our assumption that the energy lost by the washer is
Ah,
energy gained by the
yeah, but I would
water.
make it explicitly clear to the examiner that I know that no energy loss to surroundings. Huh? They love that sentence.
Yeah,
No to surroundings. So what did we? What are the key takeaways? What the equation about the mathematical formula and that connected. Actually, this you can go in a kind of feedback process. You can get here if you notice that you can add it back and then kind of iterative process to write an
yeah,
right. Coals are used for fire walking, typically glow dull red with the peak energy emission taking place. Wavelength of two. So wavelength given, um, and they're asking the part of the spectrum. And they said dull to micrometer. What is your strategy for identifying this?
yeah. I would use Wien's law because they've given a wavelength.
Yeah. What are the wavelengths you know in that region?
Um, of 2 micrometers. So that's 2 in 10 raised
No, no,
to
I'm
6.
asking what are the wavelengths you know? What is the wavelength of visible light?
Oh, that's I'm not sure.
That's in hundreds of nanometers. So we can take like 300 into 10 to the power minus 9, that is visible. In terms of this is in nanometers. No? Nanometers. So in terms of micrometers, that would be what the hell?
3
Point,
micro nano.
point.
Yeah, point 0.3.
Now we are looking at something higher than that, higher wavelength than visible light. So if we have here, that this side is the highest wavelength. That means higher than the highest wavelength. Like this is somewhere in the middle, but micrometer is somewhere all the way here. That means beyond red. Is that beyond violet is ultraviolet, beyond red is
It's radio waves, as
infrared.
in
No, because
infrared. Yeah,
no, you can't go to radio waves because that means your electromagnetic spectrum knowledge is a little off. The microwaves, microwaves are approximately like centimeter range, and radio is commonly kilometer range, right? It's in the scale of centimeters and kilometers, nowhere near micrometers. All right.
yeah.
Mm, So that's infrared body, 1 mark, so no issue. Peak wavelength corresponds to black body temperature of 1500. Tell me the formula.
So lambda max is equal to Wien's constant over temperature, or rather, show that peak wavelength.
Yeah, they're asking you to find the temperature, no? Temperature
Yeah,
equals
so it's
over
lambda max.
directly getting Kelvin, right? You can give the reverse. If you are given the temperature in, Celsius, and you have to find the lambda max, then you have to be very careful to convert this into Kelvin first. That's 773 Kelvin. Otherwise, this will not work. This has to be in Kelvin. Now here we don't have a problem because we are finding temperature. Wavelength is given. You directly get it in Kelvin. All right.
Yeah.
In case.
Yeah.
Then we have average radius, rate at which energy is radiated. What equation is that?
Flux.
All syllabus flux. Syllabus intensity.
Right. So the flux is equal to lum.
Not that. Yeah, you are thinking flux equals luminosity over 4 pi d square. That is for if you are measuring flux at this time.
Yeah, for sure.
Okay.
Could you say that again? Sorry.
Now flux equals luminosity over 4 pi d square. By the way, in syllabus it's referred to as intensity, but so if you're using this flux thing means the power per unit area some distance away from uh, the object.
Yeah.
But what we want is the luminosity. That is the power. We don't want power per unit area here. No. We want power rated energy.
No.
Luminosity is power. So something with luminosity and temperature.
Yeah. So that can be. Yeah. So that would be luminosity is equal to 4 pi r square sigma t raised to 4.
So that R will be this value. What is there? They're given 2.5 centimeter. Right? So that's 4 pi times 2.5 times 10 to the power minus 2 whole thing square times ambient temperature 1000 something around
500.
Yeah. So we'll be able to calculate that. That's no problem.
Yeah.
That, like, but equation selection is very important. Huh? Did you get this one? Can you use this?
Yeah. So that formula is to show the luminosity per power area, and that's when of an object radiating to another object, light, and then that's to find the distance between.
Yeah. So just to elaborate and maybe yeah, this is the radius of the in this formula. This is the radius of the object that is emitting the radiation. This is also in meters, but this is the distance between the object and the observer. Some distance away. In the case of stars, the distance may be huge, like thousands or millions of light years away. So again, one more thing. This one is measured quantity is temperature. This one measured quantity is the flux, right?
Yeah.
Then we have shape of a spectrum for radiation emitted. And the second curve to show the shape for 2000. Okay. Okay. For 2000 K, you expect the lambda max to be
higher.
Are you serious right now? How can you give an answer
Right.
like, lambda max equals Weir's constant over temperature, isn't it? So for
Yeah,
this just went up. So lambda max,
goes down.
yeah. So you should never just impulsively give a prediction without considering the equation in your mind. Okay.
Yeah.
All right. Like that. Then, okay. This is lambda. This is intensity. So we know that lambda max thing will be around somewhere. The peak will be this side, but will it be lower or higher? The intensity.
Right. So that's lambda max intensity. So
Lambda,
that's
lambda max is lower, fine, but intensity.
it would be. Let me look at the equation.
What is the equation that you can use?
Um, yeah, flux is equal to.
Yes. So at a given distance, at a constant distance, flux is higher. If the luminosity,
Luminosity is
yeah. So then between 2000 and 1500, which one has the higher luminosity?
2000.
So then we are looking at something higher than this. So maybe
Yeah.
so either that or even
Yeah.
if you see it when studying, this shape is very apparent.
Yeah.
Something like this in the Shravan notes pictures also. Then we have a number 5, very easy thing, mass given, specific heat capacity given. Okay, just the delta, no. Okay, they're asking the increase in temperature. Might be interesting, but here the interesting part comes in the energy, no? Can you tell me formula for the
Yeah.
energy? We'll just do that and move out. The energy
Yeah.
is how much?
MC delta
Yeah,
T.
but the energy now they said no. Look at the numbers and tell me. I think they say car of mass 1200 kg, traveling at speed 25 ms minus 1 during.
Oh, so it's kinetic energy is converted to thermal energy.
Read the question properly. Tell me a formula. Now I'm going to start writing. You do any corrections? Huh?
Yeah.
Half mass velocity square. Am I done on the energy side?
Into 20. No, you're not because it's 25% of kinetic energy. So
Right. So I'll multiply this by 0.25 or 25 over 100.
yeah. Yeah.
Then only we put the and we are looking at the increasing temperature, so very easy.
Yeah.
And we won't waste more time on this.
No.
Then yeah, when your diaphragm contracts, the pressure in the chest cavity is lowered below the atmospheric pressure and air is forced into your lungs. Okay. Diaphragm contracts and lung capacity increases by 20. State 2 assumptions you would need to calculate the new pressure if the initial pressure is known. Okay, what is this related to now? This is the first gas question we are doing, right?
Yeah.
So what is this related to?
Well, we have the equation for the gas, right?
Yeah. So tell me.
So pressure into volume is equal to NKT.
Yeah. So now, are you aware of the three separate sub laws that you can extract out of this?
Could you remind me of them actually?
So when you have number of particles and temperature constant, we have PV equals constant. That's called Boyle's law. So that one tells you that V1 equals P2 V2 because this side is a constant. So whatever multiplication of these two will be a constant. That's why you can equate, P3, V3, P4, V4, whatever multiplication of them constant. On a graph, it appears if it's P against V, it's a hyperbola. If it's P against 1 over V, it's a straight line. Then what else? What else? How do you prove it? If you are given this graph, you take about 3 points and you show that you literally obtain the data, multiply them, and show that the value is constant.
Right.
If you are given like a graph with numbers and everything, and say using data from the graph, prove that Boyle's law is obeyed or the pressure is, this one PV equals constant. They might give this in the paper and tell you that to show that this is true. So you have to kind of take values, pairs of values, multiply them and show that this PV product is constant. Okay.
Right. Yeah.
The pressure law that tells you that when these ones, volume and number of particles are constant, pressure is inversely proportional to temperature. Directly proportional to temperature. But we can summarize it as T1 over T1 equals T2 over T2. Yeah, these two are in Kelvin. Okay, the temperature are in Kelvin.
Yeah.
Then we can also have the situation where volume proportional to temperature. So V1 over T1 equals V2 over T2. But among all these three laws, the common thing is you take two quantities and make the other ones constant. So here, if you are dealing with pressure and volume, right, number 6a, lung capacity increases by 20%. We want to find the new pressure. So we can, we can calculate the basically pressure into volume equals pressure 2 into volume 1 times 120 over 100. That has increased. So we have to find this one. So in order for that to happen, what are the two assumptions?
That temperature, number of molecules are, number of particles are constant.
Yes, and that those are the it's two assumptions. Then volume inhaled is that much. It's given 2.5 to 10 to the minus 4. 25 breaths per minute, mass each second. Okay, Jesus Christ. Okay, I don't know how you would do it. Can you tell me your approach, please?
Yeah, I see the equation for kinetic theory, but this is a 2-mark question, so it's not as in that's not related. So
Yeah, it's not from there. Why have they given density?
oh yeah, so density is equal to mass over volume.
That's what you need to focus on. So mass equals density times volume. We have density.
Yeah, that's 1.2, and then that's times 2. Yeah.
Think. They're asking mass each second.
Each second. So yeah, so 25 divided by 60, that would give 1 the breaths per second. And then I think that I would multiply with the mass, which, yeah.
Yes, we are looking for mass.
Yeah.
Multiply by mass, but mass is not known.
Yeah, but we find it, right?
Yeah.
This
For mass, we can't put mass here. Read the question and see what else is given.
25 breaths per volume is given.
That's what we are trying to put here, volume, right?
Yeah.
That's 2.5 times 10 to the power minus 4. So another person may rationalize like this, no? This is the volume per minute. Volume per minute, then dividing that by 60 will give you the volume per second. So volume per second multiplied by the density gives mass per second. No? See?
Yeah.
Yeah. Somebody else might divide both sides by 9. So put the mass per second here, volume per second here, right? That is how you might want to rationalize that. So, okay, you'll get that answer anyway.
Yeah.
Without a doubt, we can get it. Then body temperature 37, outside 20. Calculate the rate at which energy is used to warm up to body temperature. So we are actually dealing with again. What is the equation? If specific heat capacity is given,
E is equal to mc delta theta.
So that should be automatic. Huh? As soon as you see that, so the delta theta is 17.6. Yeah, specific heat capacity, that's 1000.
And mass from previous part.
Yeah. Whatever it is. And then actually we are looking for energy over time. That's why we are substituting mass flow rate. Divide both sides by T. And substitute what we have in the previous one because that's mass per second. And we directly get the power. Okay, that's that worksheet done. That took a long time, more than I expected. But we covered a lot of topics, no?
Yeah.
Actually, I'll be doing more of this and just posting.
Yeah. Okay.
Even after this class, I have to sit down and do it. Okay, what else can we discuss now?
We are
black body radiation, gravitation, space, radioactivity.
I would say maybe we can do black body radiation, or because we're already in that topic kind of, or maybe.
How about this? What is this called? What about simple harmonic motion?
Yeah, let's do that.
That's also a crazy topic, no? But
yeah.
I don't know. Speed revision can be done. No, I'll work on that separately. So, there's a bunch of, there are so many things to choose from. Huh?
Yeah, I mean, there's ideal gas law kinetic theory questions.
Ideal gas law is pretty much okay because it's the Boyle's law, that pressure law, those things to be applied.
Yeah.
I wouldn't say it's complicated. It's just application of equation. But now Black body radiation. Okay, since you mentioned, we'll just go over it a little bit and see what we have there. Black body radiation.
Which one?
Open response question. There's only one open response. That is called 30. Wait, wait, wait. Yeah, 31. 31
Yeah.
radiation QP. It says open response, huh? Paper type open response.
Yeah.
Yes. Okay, what do you have here? This graph looks familiar. It looks like a VN graph. Are you on it? On the paper?
Yeah, I'm on it now. Yeah.
Okay. Give me a second, please.
Yeah.
Yeah. So this is a VN graph, then peak radiation flux wavelength, we can.
Yeah, that's simple. Go up the graph and then that's 18 micrometer.
Okay, nice. So then, good job spotting the micrometer. So temperature also you can calculate from the VN, no?
Yeah.
That's all right. Circular orbit, average speed cannot be determined directly. Extra data values to calculate orbital period. It's think about the orbital period is capital T. T equals
2 pi by omega.
now we have radius. Radius. How do we bring that? 2 pi by omega. Total period of the asteroid. What the hell? Asteroid is in a circular orbit of known radius. R is known. We to calculate the orbital period of the asteroid. Why do we need two things? Why can't we just know the
Yeah, because V is equal to R omega and omega is equal to V by R. But we know the.
I'm very confused. How to are you getting any ideas? I'm thinking like if you know velocity or angular velocity, you can calculate it. You don't need any other value, right? Why do you need two values? I wonder. Then you just can you read in the beginning of the question and see what you get?
Yeah.
Um, okay. Wow. This lasts for two refills.
Oh, yeah.
That's pretty cool. One bottle. Usually you can't get this much from a normal one. All right. Okay. Hold on. Now, okay. Temperature of the asteroid that is not related to circular motion. Um. Got it. I got it. So if you're going to use the radius, we better use omega equals T over R.
V by R. Yeah.
So T equals 2 pi R over V. that we can rationalize as being the circumference divided by orbital velocity. So we can say God damn it. How about angle? Because I know theta over t is equal to 2 pi over capital T. So
But you have a point there because theta is equal to. But that's strange because it's. Uh,
this is the thing. This is the thing. We don't have to overcomplicate it. This is omega actually, but instead of omega, we can put theta over t to make it into two things, right?
yeah.
So we need to like know the angle travel by the asteroid and the or the time t taken to travel an angle theta around the sun. Right?
Hmm.
Those are the two criteria. Time t to travel an angle theta um, around sun. This is quite strange, isn't it? Something we are not that familiar with. Like,
Yeah.
but the key to solving it, I think, is once you identify that it's 2 pi over omega, you figure out to find omega, what would you do? Right? We are
Yeah.
using supplied in the question, but in reality, astronomers have to find it, right? So you think in perspective of astronomer to see what they will measure.
Hmm.
Right. Okay. The asteroid is 1.5 times 10 to the power 11 meters from the planet Jupiter. Calculate the magnitude of the gravitational field strength of Jupiter at this distance. Okay. Magnitude of gravitational field strength of Jupiter at this distance. Okay. That's all right. We already know the equation, no? Do you?
Yeah. Yeah. That's F is equal to mg, and then substitute to find. We have m, and we need to calculate f.
Yeah. If how do you calculate?
mv square over r. That's no. It's an asteroid, right? So it's gravitational
Easy. Look what you did there. mv squared over r is what kind of force is this? Centripetal.
centripetal.
And you equated that to mg, saying that basically what you are saying is the gravitational acceleration is the centripetal acceleration. That might not be a
No, that's not smart.
that might be actually kind of smart, but actually we don't have the velocity. That's the problem. Okay, that is not wrong, but we need to look for some things that we know. Here,
Yeah.
when they say gravity, right? Um, you should know that there's an entire section of the data equation sheet, you know, dedicated to gravitational stuff, right?
Yeah.
Right. So, what do you have there in the equation sheet under gravity?
Yeah. So F is equal to G capital M small m over R square.
Do we also have something for simple g?
Yeah. F by M.
There we go. So that means this by m. So we are not interested in the mass of the asteroid. That is can
No.
we have the mass of Jupiter and r square. So we can just substitute and calculate because radius is given, no?
Yeah. But this R, yeah, the R square is.
Then they can, after that they can ask about the velocity, you know, like
Yeah. But in this case, right? Yeah. Sorry.
yeah, please tell.
No, but like in this case, or in general, the R square is the distance between the center of the two masses, right?
Rather, r is the distance between the two masses, and here the asteroid is one mass, and Jupiter is the other mass. So this is the r, right? Sometimes you have to be
Yeah.
helping with the, you know, sometimes instead of giving this directly, they can give you this distance from asteroid to the surface of Jupiter, or also known as altitude. No, altitude
Yeah.
above the surface. They may give you this and the radius of the planet separately. So you need to add them to get the total center to center distance. That's just a tip.
Yeah.
Um,
And that's the radius of orbit, right?
Sorry,
That would be the radius of orbit that we find, this R.
orbit. Yeah, no? Yeah. That is from center point of the two, between center point of the two objects. Right. Now that you find the gravitational field strength, later now in this question they are not giving, but they might give a question to find the velocity, because they are given the radius also. So then you can say the gravitational acceleration equals the centripetal acceleration in, sorry, that's v squared over r, right? There are all kinds of
Yeah.
questions that can be given here, isn't it? Because once you find the g, you can substitute it here. Radius is also known, so you can find the velocity, or they can even give you the to find the omega or the frequency of orbit they might give, no? The limited
Yeah.
so actually there is testing your mathematical ability. Square, then substitute r from the that 1.5 to 10 to the power 11 that they have given here.
Yeah.
Omega, then you can get f equals omega over 2 pi, because omega equals 2 pi f. That's
Yeah.
at this point I want to emphasize also that f, t, and ft and
Omega.
omega are part of a family of three. Yeah, if you find one, the other two are immediately, you don't have to worry about the other two. You can easily find the other two. Okay, they are part of a triplet. So in circular motion, that triplet is very important. Right? If you know one of them, you can calculate the other two without any difficulty. Right. Then, of course, regarding unit 4 connection, we can have the circular motion and gravitational, force. Centripetal force equals gravitational force and the stuff that arises from it. Now, in unit 4, we saw that when we do mv squared over r equals bqv for cyclotron type of,
Yeah.
we obtained this one, p over bq. Then also we were able to obtain f equals bq over 2 pi m, I think, something like this we obtain. So those kinds of
Yeah.
cool stuff can be obtained. So for gravitational fields also, you should be able to put gmm over r squared equals mv squared over r, and actually the mass of the orbiting object will get cancelled out. Then you can nicely cut one r and obtain some pretty interesting results, right? Um,
Yeah.
yeah. So all kinds of or omega square, we can obtain this very nice m equals r square you can obtain some nice equations from which we can kind of see that the velocity, yeah, velocity is inversely proportional to square root of rate, right?
Yeah.
Actually, there's a past paper question from this that you know, the Milky Way, you know, our galaxy is called Milky Way, right? Sun is over here. So they were asking for to predict the velocity of a predict the velocity of another star that is twice as far away from the center of the Milky Way as our sun, right? So using this,
Yeah.
you were supposed to say that the velocity, the tangential velocity is lower for this thing.
Yeah.
Yeah, that was a question. Then after that, that question said actually, in reality, it has been observed that the velocity of the star in the periphery is same as that of the sun.
Right.
According to the mathematics, saying that the velocity should be lower, but it is observed experimentally that the velocity is same, and that is actually due to the presence of dark matter. Because see,
Okay.
when the radius increase or the velocity is constant, you know, g cannot increase, right? Because g is
No.
constant. The mass, we assume that most of the mass, actually in the beginning of that question that I'm talking about, it was said that that most of the mass of the Milky Way is concentrated in the middle. That's why when we considered the second star, we didn't increase the mass, but actually, turns out dark matter is distributed all over the place. So that dark matter increases the mass of mass that is causing a gravitational field that is felt by the second star.
Yeah.
All right. The reason I mentioned that is because this is one of the this is evidence for dark matter that stars in the periphery of a galaxy are traveling faster than they can with the observable mass. So there must be some kind of unobservable mass that is causing the mass of the galaxy to increase.
Right. That's good.
I see. That's why I'm trying to mix like different stuff because
That's good.
right, number two. Sun behaves as an appropriate black body radiator. The peak energy radiation occurring at radial 5. Okay. Surface temperature, gas displacement of fine easy. Radiation at the top of the atmosphere. What is that? Kilowatt per meter square. What do you identify it as?
Right. Kilowatt per meter square. So that's luminosity per area. So flux.
Ah, very nice. In the new for the like now I'm going to put this on YouTube for the new syllabus people. This is intensity, right?
Right. Yeah.
I'll be sharing this video with two of my other students, and probably their Zoom calls also. I will be recording and uploading and sharing among you guys. Okay, not a problem.
Yeah. No. It's good.
So we can cover some more stuff.
Yeah.
Okay, so then once the intensity is given, immediately you can recall the equation. No? That means
Yeah.
flux.
Luminosity over area.
There you go. 4 pi d square. Tell me the value of d from the question.
That's 1.49 into 10 raised to 11.
That's right. Hence, calculate the radius of the sun. Okay, what are luminosity? No. Okay, once you know the luminosity, with the radius.
Right. We can use Stefan Boltzmann's law. Yeah.
Okay, so we managed to get some space questions also in here. That's good, I think, because yeah, you can't learn radiation without space. No? So anyway.
Yeah, in general, I think it's always the questions that test your application to situations that makes it like calculations. You have to, of course, read and you figure out, but it's mostly the explanation for why things happen.
In these Save My Exams worksheets, I think inside the worksheets, a lot of questions repeat because most topics are, they don't stand alone, they are intertwined, right? Right.
Yeah.
Now, huge power output of the sun due to the nuclear fusion. Okay, within the core, state and explain the conditions. There we go. This is a nice question. I put this in the WhatsApp, the study points also.
Yeah.
Yeah. What do we need? The statement, please.
Yeah, sorry, the file got closed. But
the temperature is required. Yeah. 1 second, please.
Yeah.
All right. Yeah, first condition.
Wait, sorry, it was the black 31, right? Black body radiation.
It was 31, yes, 31 QP, not the MCQ, but the regular one.
Yeah, okay, I'm with you now. So part B, right?
Yeah.
Right. So the statement is high temperature and pressure, and the reason for the the reason for high temperature is that when as the temperature increases, like temperature and pressure are related, right? So if
no, let's not struggle anymore here. This high temperature, what you need to know is EK is proportional to temperature, like we discussed at the beginning. This is also related to that what we were talking about the melting metal or something.
Yeah.
Yeah, when temperature increases, kinetic energy increases. So when kinetic energy is high, kinetic energy is required by
to fuse the nuclei together.
No. Related to unit 4. Overcome
the electrostatic repulse. But it's
right. Why do you need a high pressure? Now, instead of high pressure, you can also say high density.
Okay.
Those run hand in hand. Those two run hand in hand because you can't increase pressure without increasing the density. But why is that? I think to increase collision because we don't want fusion events happening once every 3 years. We want it happening many thousands of times per second, and it will only happen if they have a chance of colliding. Even if they have high kinetic energy, they are not confined to a small space, then the reaction rate will not be appreciably high. All right. It's something you need to memorize, nothing to rationalize in the exam. Don't waste time rationalizing and building the story. because
Yeah.
these are the statements, these are the corresponding justifications. Like nothing to think about, just study and regurgitate. Then,
Yeah.
okay, we have power radiated from the Earth. What? Earth can be considered to be a black body radiated at a temperature of 25. That's stupid. Total power radiated. So that's okay, no? Which equation?
Flux is equal to luminosity over area.
I will let you analyze that and see whether you are correct or not. Okay. Um, are we talking about something observing Earth, or are we talking about energy released by black body, or released by black body and observed from a third party? Sorry, observed from a different place. What are we talking about here?
It's
You don't have stuff to substitute here. What will you substitute for flux here?
we we don't have
Yeah. Do you realize the
anything.
point? Like I emphasized before, this physics related to the object is the physics related to the object is L equals 4 pi I 4 pi r square 4 pi r square sigma t4. Then when somebody is observing from a distance at a distance of d, then here at this place flux equals L over 4 pi d square will apply because the
Okay.
power here is spread out. It's like uh, it's like music spreading away from a speaker. The further you are, the lower the volume. So here, further you are, lower the brightness that you will see. This equation is for when you are looking at the black body from a far away place. This equation is for when you are the black body. All right.
Right. Yeah.
So not this equation.
Yeah.
4 pi r square sigma t4. And
Right.
I want this solved now. R is fine. 6,380. Tell me if I make a mistake. I might make mistakes on purpose.
Yeah. So the R has to be squared, and then the yeah.
R has to be square. That's all. Any other error? There are
Um,
there are two more errors.
right. Shouldn't the temperature be in Kelvin?
Good. Very good. Then
Um, oh yeah, and radius is actually in supposed to be in meters, so it's into
yes.
10.
Very good. Very
Yeah.
good. That's great. That's very good to see. Very encouraging. Um, wavelength of peak energy radiation for the Earth. That is, we know the law. What's the law?
Mm. Oh, Wien's law.
Yeah. And temperature you will again substitute as 298, not 25. Region.
Right.
Oh, great. Now we have to find this thing. No? You say what wavelength, what family of electromagnetic thing it is. Wien's constant is how much? I don't have my data book here.
Yeah, it's 2.898 into 10 raised to negative 3. It says M Kelvin. Is
Huh?
that milli? Why? What is the M for? It says M Kelvin.
Meter Kelvin. That's meter Kelvin because that's Wien's thing is lambda T. No? So meter
Yeah.
from Kelvin from temperature. Meter Kelvin.
Right.
That is
Yeah.
the standard unit. Huh?
Yeah.
That's 9.72 into 10 to the minus 6 I like to write it in nanometers, so that would be 9,705. That is some sick stuff. No. In this case, 9,720 nanometer. So is it in the visible spectrum?
I don't know actually.
Visible spectrum is hundreds of nanometers, thousands of nanometers. So we are dealing with a wavelength longer than any visible thing. In the visible spectrum, once again, what is the longest wavelength color?
It's red.
So something that is beyond red is
Infrared.
infrared, because we haven't still gone to the centimeter range, right? Because in electromagnetic family, we have visible, infrared, microwaves, and radio waves. We haven't come to the region yet, so it is definitely type of infrared, and that makes sense because it's just heat, right, that the Earth is releasing. So number 4 is serious, not so serious, but it's kind of cool question. Bloody hell. No, hold on. I was just scrolling through it to see what kind of other questions we have. Sorry.
That one's a bit hard, question 6. Or I just need some manipulation of data.
What, which one?
Question 6 in that of the table, with the table given.
6 or 4? 6.
6.
With that spreadsheet.
Yeah.
Okay, why don't we do 6 first then? Yeah. So what do you have? B2. Column B is temperature. Now, usually in this spreadsheet, we go from left to right. Let me share the screen just to emphasize this thing. Damn thing is not sharing. Okay. Now, usually you go from left to right. Okay, so if you're calculating temperature, you must use some data that is over here. So that is,
Okay.
yeah, how do we calculate temperature when lambda max is known?
Yeah, so Wien's law over lambda max.
You mean Wien's constant. So then what we need to write here is simply that 2.898 into 10 to the power minus 3 divided by,
Yeah.
we are calculating B2. So for B2, we
Yeah.
need to divide that by this value, that is A2.
Yeah, okay.
So what we write,
Right.
2.898 into 10 to the power minus 3, was it?
Yeah. Yeah, it is.
That divide, yeah, that divide by A2.
Yeah.
So that the value of D2 is about 0.2. D2. That is calculating area known, given that all these other things are known. So for that we will, it is simply Stephen Boltzmann law. Area.
Yeah, that's true.
2 pi r square. So area is luminosity divided by sigma T4. No?
Yeah.
So then all we need to put here is that is sigma. Sigma is Stephen Boltzmann. That is what value?
Uh, um, 5.67 into 10 raised to negative 8.
Negative 8. All right. Then that divide by the way, I'm not putting brackets here because okay, let me just put it so that there's no confusion. Divide by yeah. Wait. not that. You have to take luminosity divided by this. My bad. Luminosity for the D2 will be C2. Okay.
Yeah.
So yeah, we are looking for the C. This particular luminosity divided by these other values. So C2 divided by wait, what is it? Luminosity divided by sigma to the power 4.
Yeah. Yeah.
Yeah. So this will be times what is the temperature?
D2, right? So 4.23.
Yeah, but the column
B2.
B2. B2 is already in Kelvin, so no, nothing to worry about. B2 to the power,
4.
like I'm writing like this, you literally put to the power 4, okay? We have to show it. Then we have to calculate it literally. Okay.
Yeah, okay, but then that's fine.
Yeah. Now this luminosity would be 0.039 into 10 to the power 10 to the power 27. And this would be 4,230 because 4.23 into 10 to the power 3, right?
Yeah.
Yeah. Okay, then luminosity values to enter into the column C. Describe how astronomers could determine the luminosity of a star. Whoa, wait a second. Jesus Christ. Tomorrow at 2 you are free, no?
At 2? Yeah, that's fine.
I'm thinking like, instead of doing separate classes, why don't we just do a big like paper class?
Yeah, that would work very well.
Yeah,
Because we're all doing the same.
same thing, right? Exactly.
Yeah.
Yeah, let me arrange.
It's smarter. Yeah.
Intensity wavelength. Okay. Sketching these are fine. So then please continue doing these papers and bring up any issues that you may have.
Yeah.
All right. So for today, let's end it now. But yeah, tomorrow at around 2 o'clock, we'll start discussing some additional questions. Okay.
Yeah, that's fine. Just if anything changes, just let me know before it happens, and that's also no problem.
No, right now I have to do some communication and set this group meeting.
Okay, fine.
Yes. All right. See you then. Good night.
All right. Yeah. Good night. Bye bye.